My name is Kenny Aleben. I will present our computer graphics forum paper with the title, The Matchstick Model for Anisotropic Friction Cones. This is joint work with Miles Macklin, Sheldon Andrews, and Paul Cry. Why is our model called the matchstick model? The idea of the model started with us playing with matchsticks during a discussion about anisotropic friction. We just kept using the codename for our model. I will start this talk by presenting the core observation behind our work. Our model originates from the observation that many everyday materials have highly anisotropic surface geometry as shown in this wood example. We scanned the wood example at micron scale. The jet-colored height map on the right reveals a structure of ridges and grooves that can be described by a single direction vector. This fiber direction describes the smoothest direction of the material geometry. Before I explain how we use these fiber directions, I will just quickly recap some definitions. I will start by explaining how we represent an isotropic friction model. To describe it, I need a contact frame defined by the unit contact normal vector n. The contact plane is spanned by the tangent vector t and the binormal vector b. The isotropic Coulomb friction model is defined by this circular cone. I call this the isotropic friction cone, and it describes all feasible contact forces between a pair of materials. The slope of the cone is given by a single coefficient of friction called mu. The cone is radial symmetric, so there is no need to describe its orientation. For a given fixed value of the normal force denoted by lambda n, I can think of the cone as a 2D circle in the contact plane. I can draw this in 2D like this. The 2D circle describes the boundary of the set of all feasible planar friction forces that I represent by the components lambda t and lambda b. I will often only use these 2D cone illustrations to illustrate the friction model, as I, without loss of generality, will assume the normal force is known. I will now explain an anisotropic friction model. Here I also use a local contact frame, defined in the same way as for the isotropic case. However, the cone shape is different. It has an elliptical shape, and I need two parameters, μt and μb, to describe this shape. As I did for the isotropic case, I can look at the shape of the cone for a fixed known value of the normal force. This is just an ellipse in the contact plane. As before, I can now use a 2D illustration of the friction cone. Observe that I use the convention of having the tangent vector pointing in the direction of minimum friction. When using an anisotropic model in a simulator, one must figure out how to find the tangent and binormal directions in the world space. I refer to this subproblem as finding the cone orientation. I'll now return to talk about how the fiber directions are related to the friction cone. Imagine I take one block of material with a very clear fiber direction, as shown here. I'll now put another block on top, such that the fiber directions of the two blocks are parallel. Observe the interlocking effect of the two contact surfaces. Imagine that I now move the top block while keeping the bottom block fixed. Due to the surface geometry, I assume that there will be low resistance when moving along the fiber directions, but when moving orthogonal, I assume to feel a much higher resistance. Hence, I have a case of extreme anisotropic friction. Imagine I take another block. This time I put a block on top such that the fiber directions are at some skewed angle. Imagine I move the top block while holding the bottom one fixed. Here I assume to feel less resistant when moving in the average direction of the fibers, but the orthogonal direction would give more resistance. I have a case of anisotropic friction, but not as extreme as when fibers are parallel. I will consider one more case. I take another block of material. This time I place a block on top with orthogonal fiber direction. When I move the top block in different directions, I will assume that there are no apparent difference in resistance, as there are no preferred geometries. Hence, I have a case of isotropic friction. The core idea of our work is to make the friction cone depend on the fiber directions to interpolate between friction cases. The challenges we were facing were how to change the cone shape depending on fiber directions, how to determine the cone orientation, how to deal with a dynamic state-dependent friction cone when solving for contact forces. Later in this presentation, I will talk about how to deal with each of these challenges. For now, let us watch some examples where anisotropic friction becomes important. Imagine you are living in a house near a forest and suddenly something happens. How can you avoid that your house is destroyed? Well, you cannot change the fiber directions of the tree trunks, but if the nearby farmer plows his fields to make the ground fibers point away from your house, then this happens. The point I want to make is that by controlling the anisotropic friction behavior as a function of kinematic state, I get a lot of control over resulting animations. I will briefly cover some related work. For more details, please look in our paper. Early work used isotropic friction models. These are often discretized into a friction cone pyramid to get linear complementary problems. Recent work on Newton-type solvers use nonlinear cones directly. The isotropic Coulomb model fulfills the principle of maximum dissipation. The pyramid can be made anisotropic by assigning each face of the pyramid with a different value of the coefficient of friction. In games, this is taken to extreme using only two decoupled directions. To control the cone orientation, the cone is often fixed to one object or aligned with the sliding velocity. Limit surfaces have infinite many faces, hence they support anisotropic friction. One should be careful though, as limit surfaces are quite general and can describe non-convex cones too. This could give problems with principle of maximum dissipation. Original work did not describe how to keep track of the orientation of the limit surfaces in a general simulation setup. Friction tensors is a quite different model. It is highly expressive, but does not have an explicit concept of a cone. Instead, an affine mapping is used to evaluate the friction force directly. Under certain assumptions, one can derive a cone description from the affine map. Details are in our paper. In the general case, there are no cone and no guarantee that the principle of maximum dissipation is fulfilled. The orientation of the mapping is fixed to one of the material surfaces. A data-driven approach is taken in cloth friction. Here, a nonlinear mapping from normal forces to friction are created using free load force curves. Further, the model is quadratic in sliding velocity, but otherwise isotropic. Hence, no need to keep track of cone orientation. The number of parameters in the model depends on the order of the fitting load force curves. In comparison, our model has an elliptical shape. The shape changes dynamically depending on the kinematic state. It has a fairly low number of parameters that describe an isotropic and an extreme anisotropic cone. Further, it defines cone orientation based on fiber directions. I will now outline the details of our model. We have two bodies, A and B. A and B come into contact at a single point of contact. The common contact normal defines the local contact plane that has the unit normal vector n. The tangent spaces at the points of contact on A and B define the local space where the fiber directions SA and SB lives. In our work, we have used texture maps to store fiber directions, or we procedurally generate the fibers on the fly when they are needed. The average fiber direction is used to define the tangent vector of the contact plane, and binormal vector is computed from the tangent and normal vectors. The roll space vector that span the contact frame defines a rotation metric that transforms into the local contact space. Using all these transformations, we only need to look at the local contact space. In this space, the axis of least resistance is pointing in the x-axis direction, and the contact normal is pointing towards us. We may now illustrate the boundary of the isotropic Coulomb cone for some fixed value of the normal force magnitude. In the same way, I can illustrate the extreme anisotropic friction cone. Remember, I assume fiber directions point in direction of least resistance, so the cone will always be thinner in the tangent direction than in the binormal direction. I need to interpolate between the extreme anisotropic cone and the isotropic cone. To do this, I use the minimum angle between the fiber directions. I rescale the angle value to be between 0 and 1, and then I do a linear interpolation of the coefficients of friction. This is essentially spherical linear interpolation. One could choose other interpolation schemes. We picked this scheme in our work due to its simplicity. With the new interpolated friction parameters, I can now write the definition of the matchstick friction cone. I will now illustrate the matchstick friction cone. It will be someplace between the isotropic and extreme anisotropic cones. Here I have highlighted the matchstick cone with red color to make it easier to see. I have now presented the matchstick cone model. Next, I will talk about how to use it to solve for the friction forces. One approach is to use a proximal operator scheme. This scheme recasts the physics into a fixed point problem. This fixed point problem can be interpreted as a closest point projection problem. Here I will quickly outline how this works. First, I found the relative sliding velocity v from the kinematic relation with the contact Jacobian. Then the fixed point solution can be seen to be the point lambda that is the closest point on the cone boundary to any point on the half line starting at lambda and pointing in the negative v direction. More details are in the paper. The thing to underline here is that one must generate a cone every time one solves the proximal operator problem. That is because fiber directions are changing when objects move, so the cones are changing their shape and orientation over time. Let us go back and look at a different approach for solving for the forces. A different way to write up the cone is to use an implicit function representation like this. This implicit phi function is negative inside the cone, positive outside, and 0 on the boundary of the cone. I will assume I have some non-zero sliding velocity like before when I explained the proximal operator approach. I know how the solution looks like from the proximal operator setting. This time I will look at the gradient of the phi function at the lambda solution. I can observe that the gradient is parallel to the half line going in the direction of the negative v. I'll now define some non-negative number beta and the auxiliary vector w. This vector w will be used as a measure of whether the gradient of phi points in the same direction as the negative v direction. I can observe that if the velocity is non-zero, then a positive beta must exist such that w is 0. In this case, I am on the boundary of the cone, which means that the phi function is 0. If the phi function is negative, then I know I am inside the cone. This means the velocity v must be 0. In this case, I want beta to be 0 too, but this means w can be non-zero. This looks awful complicated, but if I make use of a nonlinear complementary function that I here just call psi to keep it general, then I can write up the complementary conditions in a quite simple and compact form. These equations are the foundation for any nonlinear complementary-based solver. Our paper contains details on how to assemble the Jacobian of this non-smooth root search problem necessary for building a Newton-type solver. Let us look at some examples. Here I show a tower. I can control the impact behavior by changing the fiber directions. The column on the right shows the different fiber directions. Observe that I can make the top come clean off or distribute the impact to the whole stack. In the left column, fibers are concentric oriented. In the right column, fibers are radially oriented. In the top row, I use small capsules, and in the bottom row, I use large capsules. Observe that concentric fibers makes the capsules jam more easily when moving through the funnel. In top row, the cylinder has up-down structure, and in bottom row, it has concentric structure. Initially, when rolling, nothing happens as expected. When speed increases, sliding happens, and the skewed structure of the plank in the left column causes the cylinder to skid off the plank. Observe in the right column that the isotropic simulation in top row appears a little unstable as the cylinder starts to wobble. The anisotropic in the bottom appears more stable. In the top, I use outward pointing fibers. In the bottom, I use front facing fibers. Remember, fibers point in the weak resistance direction. Hence, I expect top seam to collapse more easily. Observe in the top, the keystones are falling straight down. In the bottom, the weight of the keystones push the pillars outward. In this example, the fiber directions are visualized as small arrows. During an interactive robotic interaction, the fibers are changed at runtime. In this example, a car is driving from a road with good strong grip. The car makes a hard brake into a region with strong anisotropic friction. I will now briefly sum up what I have shown in this presentation. I presented a novel anisotropic friction model with dynamic changing shape and cone orientation. It uses fiber directions and free coefficients of friction to generate cones on the fly. The model supports the principle of maximum dissipation and is easy to use in proximal operator, LCP or NCP based simulators. The new model needs fiber directions. This changes the usual workflow when rigging a simulator. Texture maps or procedural generation are two approaches we used in this work. Materials that the model can handle are limited to the ones that are described by a fiber direction field on the surface. For future work, it could be interesting to take advantage of real-life photos of materials to make modeling of fiber fields convenient. The model proposed shows intuitive control. It can produce anisotropic phenomena known from real world. It could be interesting to validate how physically accurate the model is on real world data. Thank you for your attention.